Okay, so I think we're going to get started. Thanks so much for joining us today, and a big thanks to Streaming Media for giving us the opportunity to give this talk today. We are going to be discussing ABR algorithms, so how they work, why they're important, and how to optimize your stack. To give you a little bit of background, we are StreamRoot. We're providers of client-accelerated delivery technology, so we're helping broadcasters really scale to growing audiences, fortify their delivery infrastructure, and offer better quality of service. And so throughout the past few years, we've had a lot of experience with dealing with the ABR logic of a variety of players as we have integrated our peer accelerated technology into many of the most popular open source and also proprietary video players. So we've seen over the past couple of years what seems to work very well, what works a little bit less well, and what you can do to actually change things very quickly about your algorithms. So my name is Erica. I am head of partnerships at StreamRoot, and I'm joined by one of our founders and CPO, Nikolai. So to give you a little bit of more detail about how we're going to be approaching the subject, I'll be kicking off with an introduction on what exactly we're trying to accomplish, the design goals of ABR algorithms, and why this actually matters. We'll next be looking at the basics of how ABR algorithms work, the different constraints and parameters that we take into account, the process. We'll then be looking at the example of HLS.js, which is a player that we've been working with along with the Dailymotion player teams for quite some time now. So this is the open source Dailymotion player that's actually used on their platform. They unfortunately could not be with us today, but we do appreciate their input in our slides, and we'll be talking about that as an example. Next, we're going to look at the possible improvements to these basic algorithms, and for that we'll be relying a lot on some of the research that's been done recently into improving these algorithms, making them more efficient. And as a second example, we're going to take the Dash Industry Forum's open source player, Dash.js. Before finishing up, we're going to discuss a different approach to ABR logic that involves buffer levels, and then kind of just finish off by talking about the real keys to improving your algorithms and testing and iterating. So let's start off with just looking at this from a very high-level perspective. Why ABR? I think we all know that today HTTP streaming has become the norm for video streaming, and it's important to keep in mind that this has actually led to two major changes in the way that we actually handle streaming. So the first major change is we're taking into account multiple different kinds of network connections, different network conditions, and also the various number of devices that we're actually using to stream content today. So what we've done is we're encoding a single video into several different bit rates that the player can then choose from. Secondly, we've gotten away in recent years from that kind of custom transport-based protocol to a more traditional HTTP TCP stack. And so what that's done is allowed us to reach more people and scale via CDNs, but it's also kind of created a layering effect that's caused a degree of removal between the player and the underlying network conditions. And so that has given rise to the need for us to actually estimate the available bandwidth and have make that decision logic on the player side. So in terms of design goals, what we're looking at is to really optimize the viewer experience, obviously. So we've selected three main design goals that we see kind of throughout the different players as the principal design goals that we need. The first is maximizing efficiency. So we obviously want to stream at the highest bit rate possible given your network conditions. The second goal is going to be to minimize rebuffering. So what we want to do is make sure that we are effectively prefetching and storing segments before rendering them on the screen, in order to not have any buffer underrun or playback stalls. The third criteria would be to encourage stability. So limit the number of switches, which can be perceived as quite annoying to the viewer. So only switch bit rates when it's actually necessary because of changes in network conditions. To that To those four criteria, we can add, or to those three criteria, I'm sorry, we can actually add a fourth criteria that is quite prevalent in a lot of the research that's been done on ABR algorithms, and that's to promote fairness. It's the idea of fairness, to a fair allocation of network resources, and especially concerning devices that are sharing a bottleneck. And so we're not going to talk a lot about that. That's going to be, we're going to talk about it a little bit, but that's not going to be the main focus of the presentation today. But do keep that in mind. That is a primary design goal of some of the improvements that have been put out there. So why does this matter? It's probably quite obvious to all of you that this is very important, that user experience is extremely important, and that people are less and less tolerant, viewers are less and less tolerant of rebuffering, of poor video quality. And just to give some statistics from the analytics provider Nice People at Work, we see that view time drops up to 40% when there's over a 0.4% rebuffering rate. So this does matter. This has a concrete effect. The design of these algorithms have a concrete effect on your platform and the success of your platform. So to get into the basics of how these algorithms are actually built and how they work, let's start by looking at how this works in the player. We've separated the two kinds of parameters, the two kinds of metrics we're using, into two categories. The first we're going to call constraints. Hierarchically speaking, the constraints are actually going to supersede the other algorithms, the logic of the other algorithms, and most often act as a control mechanism when either we're starting up playtime or we're having a rebuffering event or need to adjust to network conditions. So they're most often a control mechanism. And the three that we've chosen as being the most important are screen size, CPU, and startup time. Next, we have what we call the trade-off parameters, which is really at the core of that kind of optimization, viewer experience optimization problem that we're getting to, those design goals. And so the first is buffer size, and the second main parameter is bandwidth. And actually, as kind of a little bit of a bonus, we're going to talk, when we talk about HLS.js, we're also going to talk a little bit about how StreamRoot handles the bandwidth estimation part of that in the context of getting segments not only from the CDN, but also from a network of peers. So that's kind of going to be a little bit of a bonus. Concerning the constraints, screen size is our first constraint. This is a relatively simple principle. We don't want the image to be any larger than the actual player size. It would be a waste of bandwidth resources and also CPU resources, because you're going to have to actually recompress the image to render it on the screen. So the player can give information as to its height and width, and the algorithm can therefore cap the bitrate accordingly. Obviously, your screen size is probably not going to be static, because you might have people switching from full screen and not full screen. So this is going to need to be checked at several intervals. And this is something we'll see with the example of HLS.js. Secondly, we have CPU and dropped frame rate. So if the device does not have enough CPU to decode all of the segments, it's going to start dropping frames. And after a certain percentage, the viewer is actually this is going to be perceptible to the viewer. So what we do is calculate a ratio of the number of frames that have been dropped because they have not had time to decode them, as opposed to the number of frames that were decoded. And what we can do is kind of ban a bit rate that creates that sort of problem. Third, we have startup time, which is, again, a very simple principle. We want to maximize startup time. So a good algorithm is going to begin downloading the first segment or segments at the lowest bit rate possible in order to give you that really quick startup time. This logic often applies as well to when we're seeking or when we're rebuffering for any reason. Next, we have our trade-off parameters that are more about our design goals. So the first design goal we had was to maximize the bit rate. So what we're going to need to do for that is we're going to need to calculate the bandwidth. And in the simplest of algorithms, this is done simply by taking the size of the last chunk downloaded divided by the time it took to download. So in the very simplest of algorithms, that's basically all they do to get the actual bit rate for the next segment. We often use more than one segment to take into account different network conditions and changes in network conditions, although this largely depends on the player, as we'll see. The second criteria was to minimize the rebuffering ratio, and for that we're going to use the buffer size. So the buffer size metric is going to regulate the intervals at which segments are downloaded and schedule the next download request depending on how full the buffer is. And so these rules can actually, the buffer fill rules can actually be adjusted to override the bandwidth, the maximized bitrate rules in the event of sudden network changes. And we're going to see that in the abort and abandon strategies in HLS.js.
So yeah, let's take a look how these principles are applied in the real-world use case. So here we're going to look at HLS.js, which is a HTML5-based media engine developed and open sourced by Dailymotion a few months ago. And since then, he has gained quite a lot of traction and is used by many broadcasters, including, of course, Dailymotion, with whom we've been working with. So HLS.js has 4 rules, like adaptive bitrate rules. 2 of them are constraint-based, and 2 of them are like the main bandwidth-based rules. So the first rule is the player size level capping rule. So what it does is that every second, the HLS.js will check the size of the player and compare it with the bitrates in the playlist. And if a bitrate is bigger than the actual size of the player that is displayed, it is removed from the list of the available bitrates to the adaptive bitrate algorithm. And of course, this check is dynamic. So if you go, for example, into full screen, the check will see it, and it will move back the hatter bitrates into the available list of bitrates. So the second constraint rule is the Dropframe Rule. So this one is also quite simple. HLS.js checks the number of drop frames and decoded frames and calculates the ratio of the dropped by decoded frames. And if this ratio over a certain period is more than a certain threshold, which by default in HLS.js is 20%, this bitrate is just banned from the list of the available bitrates, and HLS.js switches down the level immediately to get to the lower quality. So yeah, let's talk about the startup strategy in HLS.js. So actually, HLS.js doesn't try to optimize the startup time. So it's instead of getting the lowest quality first, it gets the first quality that is listed in the HLS playlist, which most often is the median playlist and not the lowest quality. So this is actually something that you can do to if the startup time is very important to you. This is one of the rules that you should check out to change how it works. So yeah, let's now talk about like the main adaptive bitrate rule in HLS.js. So it is bandwidth based, and what happens is that when a new segment is requested, HLS.js estimates the bandwidth by looking at the last downloaded segment, and very simply it divides its size by the time it took to download it. And then it applies an adjustment mechanism. So it applies a multiplicative factor to it, which is 0.7, so 70% if you are trying to go up the level, and 0.8 if you're trying to go down. This has mainly 2 effects. The first one is that very often the bandwidth estimated just by taking the size divided by the time is overestimated, and applying a lower coefficient will avoid to having too big bandwidth, which will basically cause too many oscillation, like overestimation of the bitrate. And the second effect is by having a different coefficient while going up and down. Basically, it makes it more difficult to go up a level than to go down, and this avoids the bandwidth oscillation effect that often happens in the players. So now let's see what happens if we add another way of getting the segment. So at Streamroot, we have developed a peer-accelerated technology that actually prefetches the different segment from the other people, the other peers who are watching the same content at the same time as you. And so these prefetched segments actually go into what we call a peer-to-peer cache stored on the user's device. And that is a complementary cache to the classic media buffer. And so when the media buffer needs a new segment, instead of just asking it from the CDN, it first asks the peer-to-peer cache or peer-to-peer cache if it has it. If it doesn't have it, it just gets it from the CDN normally. But if it does have it, the peer-to-peer cache gives the segment instantly to the media buffer. And in a classic bandwidth-based algorithm that we saw just before, it would imply almost infinite bandwidth, which would break, of course, the adaptive bitrate algorithm. So to avoid that, with Streamroot, what we did is that we added a new metric to the adaptive bitrate algorithm, which is the average peer-to-peer bandwidth. And as its name implies it's actually the average of the download speeds that you get from the other peers who contributed to the segment you downloaded. And as we connect the peers in a smart way, and that makes your peers be on the same ASP as you and like in the same city as you, very often the peer-to-peer bandwidth is bigger than that we have with a normal TCP HTTP stack, which makes the user actually have and be able to download a better bitrate than if you would have just the CDN only with actually the same environment. So let's go back to the last rule used by HLSGS. Which is the fragment load abort rule. So how does this work? When you are trying to download a segment, you will actually periodically check if the estimated time of arrival of the segment is bigger than the estimated time of the buffer starvation. And if the buffer starvation is expected to happen before the segment actually arrives, you will try to check if there is another quality, another level, lower level that will avoid this buffer starvation. And if there is one, you will abort the segment you are downloading and start to download this lower level. And this rule is particularly, especially important for use cases with a big segment size, like it often happens with HLS, like 8 or 10 second playlists. So yeah, just to sum up quickly what we saw with HLSJS, it has the advantage of having simple and quite understandable adaptive bitrate algorithms that makes them also easy to tweak and to improve. It handles CPU and player size constraints, which are very often forgotten by other adaptive bitrate algorithms in other players. It has a quite conservative bandwidth adjustment mechanism that avoids bitrate oscillations, but at the same time, it's not maximizing the bitrate you can have, like the max bitrate you can have. On the improvement side, as we will see just later, the bandwidth estimation can still be improved a lot, for example, by adding some history parameters to that. And as we saw, the startup time metric and constraint is not really taken into account, and this is one of the points that could be improved here. But anyway, even if it's quite a simple algorithms, it has in production with Dailymotion better performances than the native iOS and Android algorithms, which are really a lot more naive than that. And so yeah, to see how you can actually improve the algorithms, First, the easiest way is just to tweak the parameters in the player. So HLS.js has some config options that you can change, for example, for the Dropframe Rule or the player size rule to change the period or the threshold you use. But what is really amazing is you can actually write your own adaptive algorithms and replace the default algorithms we just saw. So you can replace the if-PS controller, you can replace the cap level rule, you can actually replace also the adaptive bitrate rules we saw with your own. And this is what we did with StreamRoot when we applied the peer-to-peer bandwidth. We added the peer-to-peer bandwidth into the estimation.
So yeah, as Nikolai said, this rather straightforward algorithm can actually work very effectively in production. However, there are some optimizations that can obviously improve on this basic architecture. And as we've seen in a lot of these algorithms, the download time of the last segment is not always an accurate representation of the underlying network conditions. And as such, these algorithms are not always really optimal when it comes to network fluctuations. So what we see often is that either they're very much overestimating them or they tend to be not responsive enough. And one of the most common problems observed is the problem of bandwidth oscillation, which you touched on briefly. And the oscillation that we see is a product of both the bandwidth estimation and the scheduling of chunks. So basically, when the buffer is already full, we have a period in which the bandwidth seems to be increasing because it's just not being used at all. And so the player can actually make a decision to trigger an upshift in bit rate based on this erroneous assumption that then must be corrected for afterwards. So we often see this kind of trend where it's really just bandwidth is oscillating. So in order to correct that, in this section we wanted to introduce a four-step system to achieve both better bitrate maximization and better stability, i.e. fewer switches and bandwidth. And so a lot of this is based on some of the research that's been done recently into ABR improvements. And the first three steps are going to involve the bandwidth estimation. So we're going to be estimating, smoothing, and then quantizing so we get a discrete bit rate. The fourth step then involves the actual scheduling of chunks. And of course, a lot of this is taken from the research. We'd be happy to share that with you after the presentation. Oops. So the idea is very much the same. We're going to estimate the bandwidth, but this time we're going to take history into account. So we're going to take a set of historical values from the last segments that were downloaded. We're then going to apply a smoothing function in order to average out these historical values and eliminate the effect of any sort of outliers that could bias the calculation. There are several possible average functions that we can use, averages that we can use. The harmonic mean has been put forth as one that's particularly effective because it tends very strongly towards the lower values. So we'll be more responsive to downward switches in bit rate and less responsive to upward switches in bit rate. But again, the average that you're going to be using, the number of segments that you're going to be using in this calculation is very much going to be based on your use case. For instance, if you have a live use case, you're going to want to be extremely responsive. You might be dealing with fewer segments because you're low latency, shorter playlist, et cetera. But just to keep in mind, the stronger you're filtering, the less responsive you're going to be able to be to sudden changes in network conditions. After smoothing out that bandwidth, we're then going to quantize that with some sort of coefficient in order to arrive at a discrete bit rate. And as a general rule, again, we want to be more conservative when switching up when we're at the higher and higher bit rates, and then more aggressive when switching down. And again, we see that viewers who are streaming already on a very high bit rate, jumping up to a higher bit rate is not as important as for the viewer who is streaming at a very low bit rate and could potentially switch up. And actually, as we saw, HLS.js does have a quantizing mechanism already in place. So it does take some of this into account. Finally, the last step involves the scheduling of chunks. And as we mentioned, the fact that segments are downloaded discretely and kind of at these periodic intervals, on and off intervals, creates a sort of bias that often inflates the bandwidth estimation. And to avoid this bias, the creators of the festive algorithm actually imagined a sort of randomized buffer where we're actually making the target buffer level random in order to avoid this kind of these regular on and off intervals. And so as you can see with the results that they have obtained there, it does very much mitigate the oscillation. And if you think back to our fairness criteria that we were talking about before, it does have a pretty strong case for convergence between and a fair allocation of bandwidth resources. Something interesting to keep in mind.
So yeah, let's see how this applies or not actually for Dash.js. So Dash.js is a HTML5-based Dash player which has been developed by the Dash Industry Forum and has been around for a while now. So it uses today 4 different rules, 2 main rules based on the bandwidth estimation and 2 secondary rules that are more here to handle certain edge cases. So let's take a look first at the main throughput rule. So this is quite like the HLS.js rule. It estimates first the bandwidth, but instead of taking the last segment, it actually smoothes out the bandwidth by taking the average of the last a number of the last segments, which is the 3 in the case of VOD and 2 in the case of live. And these are actually the parameters you wanna change or work with if you have different segment size or playlist size, because this is what will actually optimize the results for you. The second rule is the abandoned request rule. So it works a little differently from what we saw with HLS.js. So what happens here is that we still estimate the time of arrival of a segment when it's being downloaded, but instead of comparing it with the buffer starvation time, it just checks if it is bigger than 1.5 times the segment duration. And if it is, it aborts the segment and starts to download a new segment by estimating the bandwidth with this aborted segment we just downloaded and aborted. Then you have the 2 secondary rules. So the first one is actually the one that is improving the startup time. So it's the insufficient buffer rule. It's very simple. Basically, when your buffer is empty, it switches to the lowest quality. So it works for the startup time because of obviously you don't have any segment in your buffer when you start the video, and it also works when you are rebuffering to be able to start to download the segments the most fastest way. Then the last rule is the buffer occupancy rule. So this rule is basically a counterpart to the throughput rule when you have a sufficient buffer and that you think that you will be able to basically handle the bandwidth drop that you're having. So if the throughput rule tells you to switch down, but your buffer size is bigger than a certain threshold, which is called the reach threshold in this rule, you just keep downloading the same bitrate. And this rule is particularly good for VOD use cases where you can have a big difference between the pre-buffered time and the actual playback time. So yeah, to sum it up really quickly, Dash.js strong points. Well, first, it uses this smoothing of the bandwidth that we saw in the improvements parts, but at the same time, it doesn't use the quantization of bitrates, which would create this asymmetry to avoid the oscillation that HLS.js uses. So that's something that can be easily implemented into the rules. It also has a good segment abort mechanism to avoid buffering with like big segment sizes during network drops. But at the same time, it doesn't handle the CPU and the player size constraints we saw with HLSGS. And finally, it has a rich buffer threshold to avoid the bandwidth oscillation in the VOD use case. So how to tweak these parameters? Just like with HLSGS, Dash.js has a few config parameters you can play with without actually modifying any code. And what is a lot more interesting, you can actually extend the rules that I presented to either change them, like modify the constants that are in these rules, or actually write your own and actually add more rules, like you could add a player size rule or a FPS rule to these rules.
And before finishing up, we did want to mention that there are different approaches instead of the bandwidth calculation approach, including one in particular that was put forth by researchers at UMass, Akamai, and Amazon, which is called the BOA Approach. What's interesting about this is this algorithm relies solely on buffer size and kind of uses utility theory to make the decision. Basically, we have an algorithm that maximizes the utility of the two design criteria that we looked at in the beginning. So bitrate utility, maximizing bitrate, plus playback smoothness, so minimizing rebuffering. And then uses a multiplier to balance out the criteria and see which one is more important to you. So it's interesting in that it kind of avoids that unknown of the bandwidth estimation approach. In practice, actually, Dash.js just integrated this into their player, a form of this algorithm into their player. It's not in production yet. And it has only been optimized for a large playlist and segment length use case, so it kind of precludes live for the time being. It's proven a little bit difficult to implement in practice because of all of the different parameters, and the optimization is very, very unique according to the different parameters. But it's an interesting approach. It remains a work in progress. It's worth noting that there are several commercial players that do use a primarily buffer size based approach. We can cite the bitmove and player, bitdash for instance. But it's certainly an interesting approach, and we'll definitely want to follow that in the near future. Almost done. So to kind of wrap things up, we've seen that some of the widely used video players today actually use quite simple algorithms compared to what we've seen in the research. And above all, well, they've been rather effective in practice. And above all, they're extremely easy to tweak and to adapt and fine tune, especially the ones that are open source. So if there's one thing to take away from this presentation that we want to drill home is that, whether you just want to tweak the parameters or really make substantive changes, it's rather easy to do. And at the end of the day, what's most important is to understand your use case, to understand your audience, and to put in place the workflow necessary in order to be able to test and iterate and arrive at the solution that you want to have. So, I mean, any QoS metrics are an invaluable source of information, and a really good A/B testing setup can really allow you to make changes in real time very quickly. And that's what we've been doing with Dailymotion over the last couple months. That's what we encourage our clients to do. And you really can make huge quality improvements just by doing this and not even changing your workflow. So that's really what we would suggest. And as you can see, a lot of this is very use case specific. So if you have any very specific questions, don't hesitate to hit us up after the conference or over a beer or whatever. But if you have any general questions, we can take those now. No questions? Yes?
I see any note of the peer-to-peer sharing of the Dash player. Is that something you're planning also to implement?
So we didn't talk about the peer-to-peer sharing of the Dash player, and that is actually something that we have already integrated. Yes. But we chose to, we didn't have a lot of time. Yeah.
You talked a little bit about how
Okay. So the question was, how do we combine the bandwidth estimate with the peer-to-peer bandwidth estimate? How do we combine those two things when we're doing the hybrid system?
Yeah, so actually we just do a sum of the CDN bandwidth and the peer-to-peer bandwidth. And in our system, it's a hybrid system. So actually, for the same segment, you can have like the half of the segment from the peer-to-peer and the other half from the CDN. So we just do an average of the two metrics. Yeah.
The follow-up question. So, what I think that you mentioned in particular, so could the quality sort of bounce between the higher quality on peer-to-peer when it gets comes from there and lower quality on the regular delivery source? Is that how you conduct that?
So the question is, could you bounce back from higher quality on peer-to-peer and then down to lower quality on CDN?
Yeah, so we also have a quantizing mechanism that in the end you hit a limit which is stable. But yeah, if you have a bigger peer-to-peer bandwidth, you just switch your level up, and then you are connected to other peers who also have a better peer-to-peer bandwidth. So you actually keep in the same level if you are like with good peers.
And it's also good to note that it's rarely one segment downloaded from only peer-to-peer and one segment downloaded only from CDN. It's most often a mix that will allow it to have a kind of a steady higher bit rate. Yeah? Difficulties in including the peer-to-peer with DRMs? I'm sorry?
Yeah.
With digital rights management? Stuff from everywhere. Do you want to take that?
Actually, our system is completely agnostic from the DRMs because we are just transporting like data. So it can be encrypted data or non-encrypted data. It's transparent for our system. You're just sharing like raw data between users, and then each user still has his own key to decrypt the segment at the end in the player.
How do you take CPU into account in HLS.js?
Yeah, so the CPU is basically related to the dropped frames. So if your CPU is overused, it means it can't decode all the frames that are encoded, and this is actually how you see the CPU overload. And it's actually better to measure the dropped frames than actually measure the CPU, because the dropped frames are actually what is visible for the viewer in the end. And if there are too many dropped frames, you obviously see it on the screen. And yeah, so there is an API called Video Playback Quality, which is part of the video element. It's not implemented in all the browsers, but it does work on Chrome and Firefox today. So on some of the browsers you can still check it.
Do you have tolerances in terms of upscaling for when you're pulling when you're capping your screen size?
Tolerances in terms of upscaling when we're capping screen size? Tolerances in terms of upscaling when you're capping screen size. Well, it is checked at different intervals. So how can we scale up if we're
when you switch the level, when you are changing the size of the player, basically the checking is done every second in HLS.js. So what happens is if you go into full screen from like a small size, like a 360p, maximum 1 second later the player will see it, and it actually flushes all the media buffer, so you can instantly go to a bigger quality than what you had.
So if I have too much space between my different playlists and my screen size is right up against that higher screen, that higher resolution, is there some minimum standard that you're
Ah, okay. You mean if your like player size is in between two bit rates? Ah, yeah. In that case, you take the one that is like just above.
Slightly
But this is something actually to most probably implement into HLS.js, but because I'm pretty sure it doesn't handle it right now. Yeah. It's like, I would say it depends, but it's still less than, it's more a question of quality, I think. If you take a lower bitrate and you like upscale it, it won't render so well as if you don't scale a bigger bitrate. So it's always better to have a bigger bitrate and downscale it in the end. Mm. I would not have like the exact answer to this question. I think it's almost the same because it's just like a sort of proportional resizing of the pixels. What I can say that decoding the bigger bitrate is more CPU demanding. So in the end, having a bigger bitrate that you don't scale is always more CPU demanding.
Whether that's a problem or not is going to depend on a lot of other factors, and that's kind of the problem with CPU is you can't really target what is actually being used by the player as opposed to what else is going on the device. So it's not always the most precise science, I think, to figure out, what's the best trade-off, and that's why the drop frame ratio is used. So. So how many times do we need to implement our peer-to-peer module on different players?
Well, we did it with a lot of players. Now, I would say 5 or 6 different. But the good thing is that a lot of broadcasters are using the same frameworks, the same media engine. So, like we have several customers who are using HLS.js. We have multiple customers who are using Dash.js. Some of them, of course, are implementing their own player, but we optimized our module so we can wrap up our mechanism really fast into the player. So it takes like less than a week to actually get the work done.
Anyone else? Okay. Thank you so much.
Thank you.